we are looking at STD NMR spectroscopy in the last class, where it basically idea is that you study a weak interaction between a protein and a ligand. So, this was shown here where we see that if your ligand is constantly exchanging with the free ligand, okay, because this ligand and this ligand are the same molecule, but now there is a fast exchange. So, when I irradiate a signal of the proton in the protein, that irradiation is transferred to the hydrogen on the ligand, because they will be, suppose they are close in space, they may or may not be. We have to find some proton with which hopefully they are close, and once they are close they get transferred to this proton. Now, this proton is nothing but the same, because they are exchanging. So, what will happen if you record the spectrum of the free ligand now, you will see that this has decreased compared to no protein. When there is no protein and there is a protein, the difference you will see that this ligand would have now reduced in intensity, because the saturation here affected the intensity here. Okay. So, the main criteria therefore is that the signal from the proton or the signal from the ligand should be weak, because we are not monitoring this complex, we are going to monitor the free complex. We are not looking at the proton in the bound form, because the proton in the bound form will be very low in intensity. Remember again, tau c of the protein is very high. So, therefore, the overall signal of this system becomes very weak. So, therefore, we will not be able to study the bound form, but we can study the free form, because there is a dynamic exchange. So, what do we do practically? Therefore, take a large concentration of this ligand, because this is weak interaction, and the protein concentration is much less compared to the ligand. So, let us see this in this slide here. So, this is the same figure here, again there is a small error, this should be delta A. Okay. So, what typically we do is we take the protein in a small concentration, at small concentration, typically is micromolar, and the ligand is in millimolar. So, you see there is almost of course not 1000 times, protein will be roughly around 30 micromolar to 50 micromolar, and ligand will be around 1 millimolar. So, there is a factor of 20 or 30:1 ratio between the ligand and the protein. That means, this is really in very high excess amount compared to the protein. Okay. So, now what happens is the peaks from the ligand bound to protein is not expected, because for two reasons. Number one, it is in a very small quantity. So, it is this protein ligand complex will also be in micromolar concentrations, because of the protein itself is only in micromolar. So, this will be equal to the protein or less. Now, and that is one reason. Second reason, you will not expect to see the signal from the complex, that is in bound form, is that the T2 relaxation of this system will be very short, because the tau c of this system will be very high. So, if you recall in the previous lecture, I talked about omega into tau c is much greater than 1, and that happens for a large protein. Okay. So, therefore, these two reasons make the result in no signal getting observed from the bound ligand. Remember, protein is of course very weak in intensity, but further we will not get any bound form, because that population is even less because of this dynamic exchange. So, the spectrum will be dominated by the free ligand. Okay. So, what we do is we first record a spectrum of the ligand alone, then we add the protein, and then we get the signal from the protein. So, this is just a very brief schematic drawing of a case where the ligand signal is separated from the protein. This is normally happens all the time, but very sometimes it can happen that your ligand signal is overlapped with the protein signal, because protein is of lot of protons, proteins is not just one proton. So, this is normally a huge spectrum where everything will come from 0 to 10 ppm, and ligand also comes from 0 to 10 ppm. So, sometimes or many a times it can happen that your signals from the ligand overlap with the protein signal. So, in such cases it is very difficult to interpret the data. We want the signal of the ligand to be isolated, means separated from the protein signal. So, in such scenarios STD-NMR is useful experiment. So, as I said many a times this ligand will have aromatic signals or very downfield shifted amide signal and so on, that will help us to separate the ligand signal from the protein signal. And typically the protein signal which is irradiated now, remember in the previous lecture we discussed this, that we have to irradiate a signal of the protein which if it is close to the ligand proton will transfer that irradiation, and that irradiation of this proton of the protein is called as saturation. Okay. So, this is a standard nomenclature used in NOE. So, we saturate the signal of the protein, not all the protons of the protein, a particular signal. So, which one typically we do take? We take methyl signals. So, this protein will have methyl peaks, and typically the methyl peaks of a protein will come somewhere between -1 to 0 or 1 ppm. So, they are really upfield, means they are really separated from the ligand signals. So, ligand will may or may not have methyls, but let us say it does not have methyls close to the protein. So, the protein will have methyl signal somewhere around 0 ppm, and that is what is irradiated, and the hypothesis or the hope is that this will have some protons nearby from the ligand, and that will transmit the saturation to that. So, that is why we use the word saturation transfer. We are transferring the saturation from one signal, that is one proton of the protein, to the proton of the ligand. Now, this explains the term saturation transfer. Now, difference is there in this name, let us we will understand that now. So, this is what is shown here. So, you irradiate the signal of the protein, and that now helps in transmitting the irradiation to this signal of the ligand. So, what will happen is that this saturation transfer from protein will take place to the ligand, and that will result in the ligand signal now getting slightly reduced, not fully gone, because this is a very high population. Here there is no NOE, there is no saturation of from interaction between these two. So, this signal is still there. What has gone from here will be some amount of the bound form, which is also present here. So, by saturate, and because there is a dynamic exchange, this saturation of this hydrogen results in affecting this proton signal, and that proton signal is gone in intensity, gone down in intensity. So, you see now if I subtract this spectrum without irradiation, before and after irradiation. So, this is after irradiation and this is before irradiation, I will get a signal from the ligand which is reduced in intensity. This minus this will be somewhat reduced, and that is basically the idea of difference here in the name. I take a difference with and without saturation, and the difference, if it is not there, if there is no difference, then there is no interaction, because whether I irradiate or not, if there is no difference in the signal of the ligand, it means there is no interaction of the ligand with the protein. But if when I subtract and if I see a difference before and after irradiation, it will immediately mean that there is some interaction, because of which this change has happened. So, this is why we take the difference of the 1D spectrum before and after irradiation, and therefore, that is called as saturation transfer difference spectroscopy, STD-NMR. So, this is an example now. So, you can see this is a spectrum of a protein. So, the protein spectrum is really complex. It goes from minus sometime ppm, here it in case is 0 to 10 ppm. So, what we do is we select some peak in this zone, methyl peak. Why do we choose that peak? Because that peak is isolated, number one, because the ligand may come here or ligand may come here somewhere else. So, ligand peaks are not coming hopefully here, and secondly methyls are always in the hydrophobic core of the protein, and ligands also sometimes bind in the deep pockets of the protein. So, if we expect the ligand interaction in the deeper hydrophobic pocket, then the methyl signals irradiation will immediately affect the irradiation or signal of the ligand, which is also sitting in the hydrophobic pocket. So, that is the expectation, and that is what is done here. So, you can see that when I have a free ligand or before irradiation, let us say this is the signal from the ligand. Now, ligand signal will always be stronger than protein, because if you recall, we use, as I said, 20 to 30 times of ligand compared to protein. So, this signal will be much 20-30 times smaller, plus the T2 of protein is also very short, that will result in a very fast relaxation of the protein, and that will cause a decrease of the protein signal. So, what we will normally see is only the ligand. Now, after irradiating the signal of the methyl peak of the protein, if there is an interaction between the protein and the ligand, as I mentioned, there will be a decrease in the proton signals of the ligand. This is called saturation transfer, because saturating a methyl proton of the protein will cause a decrease in the intensity of the ligand protons. Now, if I take a difference between A and B, you see I will get some peaks which are affected because of this irradiation. Not all ligand peaks may be affected, because again remember proximity is the key here. The ligand proton should be close in space to the protein signals or protein hydrogens. If there is no signal, if they are not close by, that irradiation will have no effect. So, suppose there are some protons of the ligand which are close to the protein protons, that is methyl protons, they will be affected, that means their intensity goes down here and here, but the remaining protons of the ligand will not be affected. So, if I take a difference or subtract, I will get the peaks of the ligand which are bound to the or which are close to the methyl peak. Not only that, this difference automatically tells me that there is an interaction going on, because if there was no interaction between the ligand and the protein or binding, I would not have expected any difference. This minus this would be simply 0, because both would look the same, but the fact that there is an interaction or binding immediately is indicated by change in the intensity. So, STD-NMR thus helps to quickly find which ligand molecules bind to the protein. So, this is again used for screening a large number of drug molecules. Initially, when you do not know which one binds strongly, we expect all the molecules to be weak binders, but initial screening will help to filter out those which even are weaker than the regular compounds, and then take the one which are binding and further optimize it to make it stronger. So, not only that, as I said, it also tells us which sites of the ligand are close to the protein, because they are the one which are affected. So, this also helps us to find out which sites in the ligand actually bind or are in the binding interface of the protein. So, this is basically the idea of STD-NMR. We will look at another technique which is closely related to STD-NMR. This will be the last part of this course, where we look at how an NMR can be used for weak interactions. So, again, and remember the strength of NMR is weak interactions. So, we are essentially able to study weak interactions, which normally you will not be able to study with any other technique. So, again let us consider a case of weak interaction, weak binding. So, imagine or assume this ligand which binds to the protein, and now there is a fast exchange between these two states, which means there is a weak interaction. Now, let us say that there are two hydrogens in the ligand which are less than 5 angstroms in space, means they are closer in space and they are less than 5 to 6 angstroms in distance between the two. Okay. So, let us assume again another assumption is when the ligand binds to the protein, this distance does not change much. Okay. So, that is assumption. We will, of course, that can change here, but let us assume that this ligand is a weak interactor. So, when there is a weak interaction, the distance may not be so much or structure may not be so much affected for the ligand, and that this distance remains the same or similar, need not be have to be exactly same. So, when there is a free ligand, I remember again this is something I showed in the last lecture, for a small molecule typically this condition happens depending on your omega value, which is your spectrometer frequency, and depending on the tau c value, which is the rotational correlation time. So, for a if you are working at 400 megahertz NMR spectrometer and your molecular weight of your ligand is somewhere in this range, then this omega into tau c becomes equal to 1, then there is no NOE here. You see, therefore, you do not expect to get any NOE effect in the ligand, free ligand, because of the small size. But now here there is a strong NOE effect because of the large size, because this complex is now behaving like the ligand behaves like a large molecule, because it is attached to the protein. Okay. Even though the attachment is not strong, it is a dynamic exchange. Whenever it is attached to the protein, this complex now becomes large and the ligand behaves like a large molecule. So, that will result in omega into tau c becoming much greater than 1 for the same spectrometer. So, we are not going to change, but molecule now is larger because it has been bound to a bigger protein. So, this is 20,000 Daltons compared to 1000 Dalton, 20 times or 30 times. Sometimes the protein size is even bigger, it is about 100 kilodaltons, then the NOE is much higher. Now, second assumption, which this is one assumption means where hypothesis is that there is a increase in the tau c of the protein, which we know, and that will cause higher NOE. Another assumption is this distance does not change much, means compared to the free form. So, if it is 5 angstrom here, we expect it to be close to 5 here as well. Okay. So, now given these conditions, what will happen in a transfer NOE? So, this is called transfer NOE spectroscopy. So, transfer NOE is basically similar to STD, saturation transfer. Here we are transferring this NOE effect from here to here, because the broad idea here is that this molecule has no NOE, but this molecule has the same ligand shows an NOE effect, but it does not show an NOE effect here. So, by having a large excess of this in my sample and a small amount of this, my population of this is going to be small, but whatever NOE effect is shown here will be manifested or seen in the NOE between here, because this is a transfer between here to here, because the ligand is in fast exchange. Okay. So, whenever there is a fast exchange, this NOE effect here shows up in this molecule, even though this molecule is not in having any NOE. So, we will see this. This looks like a contradictory statement or confusing statement, but we will see how nicely this shows up in a spectrum, how we can get the spectrum of this molecule like this. Okay. So, what typically is done is a Noswith spectrum can be recorded on this complex, I mean the entire complex, once you add the protein, and as I said, the ligand is in large excess compared to protein. Typically we take 10:1, means the ligand is 10 times higher in concentration compared to ligand, okay, sorry, ligand compared to protein. So, ligand is 10:1, 1 is protein. So, now what happens is, because the free ligand is in fast exchange with the bound ligand, any NOE in the mixture of ligand and complex is dominated by the NOE of the free form. So, this is what the point is, that any NOE effect I see in the ligand complex form will be basically this NOE effect, because there is no NOE for this, and it can be observed in the spectrum of the free ligand. The NOE effect here is seen in the NOE of this spectrum, even though this one on its own does not have any NOE effect. Okay. So, let us see in the spectrum how it looks. It looks like this. So, this is, let us say there are 2 protons of the ligand, and this is the interaction with the protein shown here in a gray. Now, these 2 hydrogens, of course, here we are showing there is a difference, means this has shortened here, but normally we assume that the distance between this and this need not change. So, you can see here, so when I record before addition of the receptor or the protein, again this has been taken from this slide here from this website. So, you can go to this website if you want to have more details, but the basic idea is, suppose I record the 2D NOESY spectrum before adding the protein, that means for the free ligand. I do not expect any cross peak between A and B, because there is no NOE effect. The omega into tau c may be close to 1. So, therefore, the NOE effect is 0. So, therefore, there is no cross peak between the A and B. But moment I add the receptor or a protein and I record the spectrum again, you see there is a cross peak coming now, because the cross peak is not from this population. The cross peak is dominated by this population, but we are having more of this. So, actually the whole spectrum is actually this of the free, but the NOE effect is coming from the bound form. So, it looks as if the NOE of the free has now appeared, but actually it is not the NOE of the free form, it is the NOE of the bound form which is appearing on the spectrum of the free form. You see, so that is like a transfer, you transfer the NOE effect from here to the free form. So, that is why we call it as a transfer NOE NMR experiment. Okay. So, this is a very interesting experiment, it helps us to find out the structure of the free form. Now, from the NOESY here, remember NOESY is for structure determination of either organic molecule or protein molecule. So, from the NOE spectrum now, earlier I could not have got structure of the ligand, the free form, because there was no cross peak. So, no information of the distance, remember distance comes from the intensity, but now I got an NOE cross peak, and based on that I can convert it into distance, and then distance between A and B I can find out in the bound form, because again remember this NOE is not from the free, it is from the bound. So, I can get the distance between these in the bound form, but the idea is it is appearing in the free form. So, the distance, as I said, assumption is they should not change much, but even if they change, my information is still coming from the bound form. So, this is what is shown here. So, this is another example taken from this website now. So, here you can see again this is a ligand which is having some structure like this. There are different hydrogens H1, H2, H3, H4. Now, in the free form it is showing some spectrum like this, and there is a negative NOE. Remember NOE can also be negative, because omega into tau c can be less than 1, or then it can show an opposite NOE or more than 1, sorry. Now, but the point here is between H3 and H4 here I am not getting NOE here. You see between 3 and 4 there are no cross peaks. Why? Because 3 and 4 are although they may be close, they may not be having NOE effect. But if I add a ligand to this, now 3 and 4 are come close to each other, and because this is a large complex, the NOE becomes much stronger compared to here, and you can see now I can see a cross peak between 3 and 4 here also. This is just a two different experiment, but the idea is between 3 and 4 I am now getting a cross peak which earlier I was not seeing between 3 and 4. Not only that, I am also able to see this small peak 1 and 3, you see this between 1 and 3, this and this, that was not there here in this case. Why? Because 1 and 3 now have an intermediate proton from the protein molecule which will give me the transfer of NOE from 1 to 3. So, 1 to 3 is also showing a small cross peak, but now between this proton has gone on this side, and therefore, there is no cross peak between 2 and 3 or 1 and 2. 1 and 2 have become far away. So, you can see between 1 and 2 there is no cross peak which was there earlier here. Okay. So, basically this is the idea of transfer NOE experiment, wherein you look at the bound, you look at the NOE in the bound form, but what you are monitoring is the signals from the free form, because the signal is much higher in concentration, the ligand is much higher in concentration, and therefore, that helps us to integrate, get the indirect information. By looking at the free form, we are getting the information of the bound conformation.